Good morning, everyone. I'm Abhishek Samanto from the Physics Department of IIT Gandhinagar. So first of all, I would like to thank the organizers for giving me the opportunity to talk about my work. So the title of my talk today is Non-Fermi Liquid Transport in Semi-Metals and Strongly Correlated Systems. So here is the brief outline for my talk. So in the first part of my talk, I will discuss about the electrical transport, which is mainly studied by the Hall coefficient. So I will begin with the very basic Drude theory and Boltzmann theory, which are generally used to calculate the Hall coefficient of non-interacting models. Then I will discuss the so-called Hall anomaly in the normal state of the cuprates, which is something what the Boltzmann theory cannot explain. Then I will present a new thermodynamic formalism to calculate the Hall coefficient, and by using that we can calculate the Hall coefficient of several multi-band semi-metals and also strongly interacting models, and we can also address the Hall anomaly in cuprates. Then in the next part of my talk, I will talk about the thermoelectric transport, which is characterized by the Seebeck coefficient. And here also again I will talk about the Seebeck anomaly in the normal state of the cuprates. Okay, so let me start with the Drude theory, which explains the transport properties of free electrons. So the Drude theory assumes that the electrons behave like classical gases with no interactions and very weak scattering. So first we write down the equation of motion for the electrons in presence of electric field E, magnetic field B, and the scattering lifetime tau. Now in equilibrium, we can define the current operator as J equals to sigma times E, where sigma is the conductivity. Now unlike the Ohm's law, here the conductivity is a 2x2 tensor, which has both diagonal and off-diagonal entries. In fact, the off-diagonal entries, sigma xy, which are called the transverse conductivity, they are mainly responsible for the so-called Hall effect. And because of that, they are also called the Hall conductivity. Now, physically speaking, the Hall effect arises when a voltage difference develops in an electric circuit, which is transverse to the electric current and also perpendicular to the applied magnetic field. And if that happens, then this Hall conductivity becomes finite. Okay, so the DC Hall coefficient is defined as the derivative of the transverse resistivity with respect to the magnetic field in the limit of the field going to zero limit. And in terms of the conductivity, it looks like this. Now if you insert all the values of sigma xx and sigma xy from here, you can see that the effective mass gets cancelled out, the scattering time gets cancelled out, the magnetic field also gets cancelled out, and we obtain a very simple looking expression, which is 1 over NEC, where N is the density of the charge carrier. So this is like a miracle that although we are talking about transport, the Hall coefficient from the Drude theory turns out to be an equilibrium thermodynamic quantity, which does not depend on dynamics or scattering or any dissipation. It simply measures the density and sign of the charge carriers, and because of that it is often used by the experimentalist also. So the question is this true in general? So can we express the Hall coefficient in terms of thermodynamic variables, which is valid beyond the Drude theory also? So the answer is yes, but the answer is also not so simple. Okay, now going beyond the Drude theory, when there is weak interaction, so the system is described by the Landau Fermi liquid theory, and the transport quantities can be calculated by the Boltzmann transport theory. So the Boltzmann transport theory assumes the presence of well-defined quasi-particles, and that happens when the mean free path of the electrons is much larger than kF inverse. So Boltzmann transport theory gives us the expression for longitudinal and transverse conductivity, sigma xx and sigma xy, in terms of the Fermi function, velocity v, and the scattering time, which in general depends on k. But if we take isotropic scattering, meaning when the tau k is independent of k, so we see the same miracle that the Hall coefficient turns out to be a thermodynamic quantity again, which is independent of the scattering tau. But here it measures the curvature of the Fermi surface. So to understand this, we can consider a very simple example of a tight binding model in two dimensions. So here I have plotted the Hall coefficient, which is obtained by simply calculating the Boltzmann theory as a function of density n. So at low filling, when n is smaller than 1, we can see that the Fermi surfaces are electron-like. So the majority carriers are the electron, and the Hall coefficient is negative. At the half filling point, the Fermi surface becomes like a diamond, so its curvature becomes 0, and here the Hall coefficient also goes to 0. Now when the filling is larger than 1, when n is greater than 1, you can see that the Fermi surfaces are hole-like here, so its curvature changes. Also here the Hall coefficient sign also changes and it becomes positive. But the most important thing here is that the Hall coefficient diverges at very low filling and at very high filling, which are like your Drude theory like divergences, which happens at the bottom of the band and the top of the band only. However, there is no divergence inside the band. In fact, the Hall coefficient actually changes sign and it goes through 0 at the half filling point, which is also a manifestation of the particle hole symmetry, which is present in the 2D tight binding model. Now if you add a next nearest neighbor hopping term in your calculation, so the particle hole symmetry is broken and the sign change actually moves away from half filling, and now the sign change happens at some intermediate doping. But the important thing is that still the Hall coefficient does not diverge inside the band. However, in cuprates there is Hall anomaly. That means if you look at one of the earliest Hall resistivity measurements, for example in LASCO, where the Hall coefficient is plotted as a function of the hole doping x away from the Mott insulating or the half filling point, you can see that the Hall coefficient sign is positive here. Although I am talking about the electron side, the Hall coefficient sign is positive. Not only that, Hall coefficient shows a positive divergence near the half filling point. So this is completely a non-Fermi liquid behavior, because in my previous slide I showed that near the half filling point, Fermi liquid actually gives either 0 or at maximum like it's a like finite number. It never diverges. So this is definitely like a non-Fermi liquid behavior in the Hall coefficient. And then there are more recent experiments, for example in YBCO, where there are a lot of interesting phases. But if you look closely here, so the Hall number, which is the inverse of the Hall coefficient, that also falls linearly to 0, which means again that the Hall coefficient near half filling shows a positive divergence. So all these experiments actually show that here the positive divergence of the Hall coefficient near the half filling point is not coming from the Fermi liquid quasi-particle. So this is like a non-Fermi liquid behavior. Now in addition to cuprates, there are many other materials where the Boltzmann theory do not work. Yes?
Which was called FL star in last evening's talk.
Yes, yeah, I can talk to you about, yeah, FL star is slightly different, I think. Like heavy fermion you are asking, right?
No, FL star into weak star.
Oh yeah, yes, right, yeah. Okay, now in addition to the cuprates, there are many other materials where also the Boltzmann theory do not work. For example, there are some materials where the DC resistivity grows linearly with temperature and eventually it exceeds the so-called Joffre-Regel limits. So they are called the bad metals or strange metals and so on. So, and here the Boltzmann theory do not work. So here comes the Kubo formula for the calculation of the DC conductivities. But the calculation of DC conductivities by using the Kubo formula is very challenging, because after computing the dynamical conductivity, one needs to take several limits also in proper order. For example, first you need to take thermodynamic limit, then Q going to 0 limit, and finally dynamic set to 0 to get the DC conductivities. There are other methods also to compute the Hall coefficient or the DC conductivities, for example the perturbation theory, but here one needs to do resummation of many diagrams, particularly in the limit of strong interactions and strong disorder. High temperature or frequency expansion, where one needs to expand in terms of the operator, which is also not very easy. Imaginary time quantum Monte Carlo simulations, which suffers from analytical continuation, and also it is limited by the fact that it doesn't work well when the energy is smaller than the temperature, because it suffers from severe sign problem. And on top of that, the calculation of the Hall coefficient is doubly challenging, because we need to calculate both sigma xx and sigma xy. So the question is there a way to avoid all these challenges? And the answer is fortunately yes. So there is a recently derived formula for the calculation of the Hall coefficient, which I will present in my next slide. So here is the new Hall coefficient formula, where the Hall coefficient RH is written as a ratio of two thermodynamic susceptibilities, mainly the current correlator and the current magnetization current correlator, and both of them can be calculated very easily. There is a correction term also, but again the correction term can be expressed in terms of thermodynamic susceptibilities, which can be calculated order by order. So the most important thing to note here, that unlike the Kubo, here we do not need to compute the conductivities, we can directly access the Hall conductivity, the Hall coefficient. And this method is applicable for general Hamiltonians also, by using various many-body methods like high temperature series expansion, Monte Carlo, variation wave functions, and so on and so forth. So after setting up this formula, we first apply for a very simple case of single parabolic band, and we immediately obtain the Drude theory 1/NEC answer. Then we apply for the nearest neighbor tight binding model, where we know the Boltzmann theory answer, and we recover the Boltzmann answer that the Hall coefficient goes to 0 at the half filling point, and it diverges at the bottom of the band and the top of the band. So the next question we will ask, can we calculate the Hall coefficient for multi-band models, or particularly for the semi-metals? Why is it interesting? Because for multi-band models, the Drude theory breaks down because of intriguing Fermi surface topology and multi-band effects. Also, the multi-band conductivity calculations are very challenging, because one needs to deal with coupled Boltzmann equations with interband collision terms and so on, which is very complicated. So here I will not go into the details of the calculation, but we have set up a formalism where we can calculate the Hall coefficient for multi-band models, where we can incorporate both intraband and interband scattering terms. Okay, so we first apply the Hall coefficient formula for so-called spin split semiconductor bands, where we have two bands, and there is a band splitting which is coming from the Rasba spin orbit splitting here. And here we see that the Hall coefficient actually acquires a correction term over the Drude 1/NEC relation, and the correction term is proportional to beta square, where beta is the Rasba spin orbit splitting strength. Now the same calculation or the same answer one can obtain by doing a multi-band Boltzmann calculation, but in a very, very complicated way. Our formalism gives this answer in a very few lines. So next we look at the Hall coefficient for semi-metal meaning where the density of state actually vanishes near the band touching point. So first we look at the nodal line semi-metal, where the two bands touch along a curve which is called the nodal line. So here we find that instead of a Drude theory like divergence, the Hall coefficient actually shows an abrupt jump near this particle hole symmetric point. Next we compute the Hall coefficient for wild semi-metal and graphene. So here we see that Hall coefficient does diverge like 1/n if we incorporate only the intra-band contribution, where there is no mixing between the two bands. But if you take into account the interband contribution also, where there are enough mixing between the two bands, so then this divergence actually gets cut off. So all these predictions can be verified experimentally. So next we focus on the Hall coefficient of interacting models. So we look at the repulsive U Hubbard model, where the Hamiltonian is given by this. So and in the large U/T limit, so the low energy subspace of this Hamiltonian is obtained by applying a Gartz-Wheeler projector, which ensures that there is no double occupancy, and we obtain the so-called TJ model Hamiltonian. So in the TJ model Hamiltonian, there are two terms. So the first term is the T term, which gives a constant hopping between the nearest neighbor site, and the second term is a J term, which in its diagonal it actually gives the antiferromagnetic spin exchange, and its off diagonal entry it actually gives rise to some correlated hopping between the next nearest neighbor site. So we also find that these order J terms actually dominate when the temperature is of the order of the interaction scale. So on this model we apply our formalism and calculate the Hall coefficient. So here I will present the Hall map. So first I am showing the Hall coefficient for the 2D tight binding model, which is the non-interacting case, whose answer we already know. So here the Hall coefficient goes to 0 at the half filling point, and it shows a negative divergence near the band edge. And if you increase the temperature, so there is no change. So for all temperature, the sign change happens at the half filling point. So the same answer one can obtain by using the Boltzmann transfer theory also. So next I will present the Hall map for the interacting system for the Hubbard model. So here we have done the high temperature series expansion at higher temperature which is supplemented by a quantum Monte Carlo simulations at lower temperature between the small t and small j. And by combining these two methods, we have explored the Hall coefficient over a large range of temperature. So here we are seeing that the Hall coefficient actually shows a positive divergence near the half filling point, which is associated with an anomalous sign change at some intermediate doping. Now if you increase the temperature, you will see that this anomalous sign change moves from this intermediate doping to half filling point, and when the temperature is sufficiently large, when the temperature is much larger than the interaction scale, then this anomalous sign change actually goes back to the half filling point, and you essentially goes back to the non-interacting picture. So the summary of this slide is that, so by using our formalism and by doing this high temperature series expansion and quantum Monte Carlo simulations, we find that there is a positive divergence of the Hall coefficient near half filling, which is associated with the anomalous sign change at some intermediate doping, which is exactly seen in Q-plate experiment, which I shown in my previous slide. Okay, that's all about the Hall coefficient. Now in the next part of my talk, I will talk about the thermoelectric transfer, which is characterized by the Seebeck coefficient. Now the Seebeck coefficient is defined as the voltage difference which is developed in an electric circuit when a small temperature gradient is created. Now the transferred quantities can be calculated by using these familiar relations, where J and JQ are the electric and thermal current. L is a rank 2 tensor whose different components give different kind of conductivities. For example, L11 is electrical conductivity, L22 is thermal conductivity, and L12 is thermoelectric conductivity. So the Seebeck coefficient is defined like this. Now we are again interested in the thermodynamic formalism. So there is something called Kelvin approximation, which takes care of the slow limit. That means you first set the dynamics going to 0 and then set the Q going to 0 limit. And by using the Kelvin approximation, you can write down the Seebeck coefficient in terms of the thermodynamic variables only, which is in terms of, let's say, entropy, many-body density, and so on and so forth. So we use this formula and compute the Seebeck coefficient. But here again, experiment shows that there are Seebeck anomaly also. That means if you look carefully, so near the half filling point, so the Seebeck coefficient again shows a positive divergence, which is associated with the anomalous sign change at some intermediate doping. So the question is, can we theoretically understand this? And many such materials actually show this universal feature. Okay, so we take this Kelvin formula and we consider the repulsive Hubbard model, and we do a quantum Monte Carlo simulation and calculate various thermodynamic quantities and compute the Seebeck coefficient. So first we look at the entropy. So here is a cartoon picture of the entropy. So here I am plotting the entropy as a function of doping for different interaction strength. So you can see that when the interaction strength is weak, entropy has a maxima at the half filling point. Now if you keep on increasing the interaction, you will see that beyond some critical interaction, you see, so this maxima at the half filling actually goes to some intermediate doping. So this maxima goes here, and this maxima at half filling actually changes to a minima, and that must go through some inflection point. So we note that this new maxima at the intermediate doping is precisely the location of the anomalous sign change of the Seebeck coefficient, and by this appearance of this inflection point beyond this this critical interaction strength, we can also find the critical interaction strength by tracking the second derivative of the entropy. So here we plot the second derivative of entropy in the TU plane, which is a phase diagram of the Seebeck anomaly, and we see that whenever this is 0, above that there is always a Seebeck anomaly. That means if you, for example, look at a fixed temperature, so above this point there is always a Seebeck anomaly. So this gives us the critical interaction which is required to obtain a Seebeck anomaly. And we also note that this anomalous sign change of the Seebeck coefficient or the Seebeck anomaly corresponds to the interaction driven metal to non-Fermi liquid crossover. And finally we plot the Seebeck coefficient as a function of doping or the density for a fixed temperature for different interaction scale. And here again we can explain the Q-plate experiment that the Seebeck coefficient diverges near the half filling point, and it shows the anomalous sign change at some intermediate doping. So here is the summary of my talk. So in the first part of my talk, I have shown that we have developed a new thermodynamic Hall coefficient formula. By using our new formalism, we can calculate the Hall coefficient of several multiband models, particularly the spin split semiconductor bands, semi-metals, which are nodal line and wild semi-metals. Then by using the high temperature series expansion and quantum Monte Carlo, we have calculated the Hall coefficient of the Hubbard model, which also explains the Hall anomaly, which is seen in normal state of the cuprate experiment. Then in the next part of my talk, I have talked about the thermoelectric transport. By using the thermodynamic Kelvin formula, we study the Seebeck coefficient in strongly interacting models. We can also explain the Seebeck anomaly in cuprates, which can track the thermodynamic quantities at half filling, and which is also related to the metal to non-Fermi liquid crossover. So with this, I would like to end my talk, and thank you for your attention. Yeah.
So today theory you said that Hall coefficient should be 0 at chemical potential 0, or
No, I didn't say that. So I said
the mathematical plot for the square lattice and this thing that
yes. Here, for example, yes.
This one.
So I said that at half filling, the Hall coefficient should go to 0.
Okay.
Because there is a particle hole symmetry.
Now, okay, so it is nothing to do with the chemical potential.
It has to do with the chemical potential, because
so
by
that's
tuning
right.
the chemical potential, you can change the filling.
So particle hole symmetry, or I think it is the chemical potential which matters.
Yes.
Okay.
Meaning,
Now,
by tuning the chemical potential, you can change the filling. I mean, you can go to half filling or lower filling or higher filling. Yes.
okay. Now, latter part of the talk, that divergence was related to interactions.
Yes. This is what I
So
showed.
you attributed that non-Fermi liquid, that is all, but your white semi-metal, that is non-interacting.
Yes. There is no interaction. So here we have just taken
divergence.
No, in wild semi-metal we are seeing something very strange. So here look at this solid line. So here we are seeing that the Hall coefficient shows a jump near the half filling point, not divergence. This is not we are getting. We are getting the solid line. I have just compared with the Drude answer, which we are not getting.
So there's a question.
Yes.
So the new formula for the Hall coefficient which you had,
Yes.
you had some, so this you write it as some RH0 plus correction. So is it like a expansion in some kind of in some parameter?
No, it's not a like attribution expansion. So I mean basically like it's a higher and higher order commutators. Like here you can see that there are like commutator between MJX, magnetization and current. So there will be like larger and larger commutators. So one needs to really compute that and see whether they are falling, decreasing or not.
Have you truncated the
Yes.
here, or is it an exact answer? That's the question.
Right.
I assume that the results you showed are for the leading order term later on.
This is an exact answer provided you include all the correction terms.
Yes, but the results you showed.
Right. So we have like computed the correction terms also, and we have checked that its like contribution is very small. So that like always we do.
I see. Okay. So you have checked that. Okay.
Yes.
You truncated the series, but you checked that.
Yes.
Okay. I see.
Any other question? So it's not conductive.